Hello, Algebra 2, how we doing? We got our last lesson of graphing trig functions. And today we're taking a look at the tangent function. We have yet to graph tangent. If you recall, the tangent function is sine over cosine, or opposite over adjacent, whichever way you want to think of it. And these were some of the trig values that we've seen before. And you'll notice as we, oh, it's kind of behind my camera, I apologize. You'll notice that as we go along the circle here, these numbers, root 3 over 3, and then 1, and then root 3, the numbers getting bigger. And due to the fact that tangent is opposite over adjacent, if you draw a triangle here, I can make a triangle that is like infinitely tall, right? And what I'm trying to point out with that is that, if I can make a triangle infinitely tall, well then when you do opposite over adjacent, if the opposite side is like frickin' ginormous, well then tangent could be infinitely large. Yeah? It could be infinitely large as I make the opposite side so much bigger. Like I could have a triangle that's 1,000,000 tall and then has a base of 1, right? Then tangent would be 1,000,000. And with that point being made, yes, tangent is a function that doesn't bob up and down. Tangent is a function that goes, oops, you can't see it, that goes like so. This is the tangent function, okay? And let me pause. Okay, so this is the tangent function. And so this is, I'm drawing a triangle here. And this is the opposite side of the triangle. And this is the adjacent side of the triangle. And so as you get closer to 0, your adjacent side is longer. And your opposite side is getting shorter, correct? So tangent gets smaller as we get closer to 0, okay? And then it gets bigger as we get closer to 90. But the thing is when we have a flat angle that literally 0 degrees, then the triangle is 0 tall, and the adjacent side, right, is say 1. So 0 divided by 1 is 0, which is why tangent of 0 is 0. But when you have a triangle that has no base, okay, so like as I continue to draw in these triangles, the opposite side is a little bit bigger and the adjacent side is a little bit smaller, and the opposite side is a little bit bigger and the adjacent side is a little bit smaller. So tangent keeps getting bigger and bigger and bigger. But then all of a sudden you just have a straight up and down line. Well, now so now the opposite side is say 1, and then the base is 0 because it literally doesn't exist. It's a straight up and down line. So over here, if I change colors, where the height didn't exist, tangent was 0 because 0 divided by blah is 0. But here, the straight up and down line, the opposite side is 1, and then we're dividing by 0, and that means it doesn't exist. Okay, because you can't divide by 0. So here you can see there are asymptotes, as they're called, at pi over 2, because I can't divide by 0, right? I can't divide by 0, and that's what's happening there. And then we have another asymptote at 3 pi over 2, and so on and so forth. It continues to repeat just like every other function. So you don't have to be a tangent expert per se, but what you need to realize is that the graph has this lovely looking curve and has asymptotes at pi over 2, negative pi over 2, 3 pi over 2, negative 3 pi over 2. Okay? And it's happening If you're a fan of the unit circle here, it's happening at these moments when your line would be straight up and down. It's not happening at these moments where your line would be horizontal. Okay? When it's horizontal, that's where your function is 0. Aquí and aquí. Okay? I know I end up spending a lot of time on Desmos, and I apologize, but I just feel like it really solidifies things. So everything about tangent is the same when it comes to all of these transformations, okay? The vertical shift, the phase shift, the yada yada, everything is the same, okay? Except for one thing and one thing only, and that's the period. The period is different, all right? If you take a look here, this function repeats itself every pi, right? The distance between pi over 2 and negative pi over 2 is pi. This squiggle is repeating more often. Like, take a look. If I plot cosine and compare the two, you can see here how it takes so much longer to repeat itself in comparison to tangent. Like, look at tangent. It starts way down here and goes up, and the cosine only does half of its curve. It's still got another half to go. Okay? So tangent is like twice as fast, so to speak. Okay, so I just quickly made some notes here. This was the typo. This should say pi over b to help find the period. And I said treat tangent like you would anything else when it comes to these transformations. But just keep in mind there's no amplitude for tangent because, well, the amplitude means like, you know, how tall the function is. This function just goes on forever. So there's never going to be an amplitude because it just goes infinitely up and down, okay? So that part doesn't really matter anymore. And the period is pi long instead of 2 pi long, okay? So we want to keep those things in mind. Desmos is obviously going to be our best friend here. And I think the important part is to just keep in mind the asymptotes. So I wrote here that the asymptotes occur, that start at pi over 2, and then if you add or subtract, I should say, pi over and over, you'll find the other asymptotes. Let me show you what I mean. Here's pi over 2. But if you add pi to that, you're going to get to 3 pi over 2. If you add another pi to that, it's going to put you at 5 pi over 2. If you add pi to that, it'll give you 7 pi over 2. So starting at pi over 2, every pi, and why is it every pi? Because the period length is pi. So the asymptote is sort of the beginning / end of the period. You could also do negative pi over 2 as the beginning if you wanted. That's the beginning / end, and then every pi, the asymptote repeats itself, okay? So with this graph here, we're changing the period because the b value is 2. So our period is now pi divided by 2. That is our period, okay? And our vertical shift is up 3. That's what these two things tell you to do, okay? Pi over 2 is your new period, and the plus 3 tells you to move up 3. So without being too scientific, okay, we just know that if the period is happening sooner, then so is the asymptote, right? So where the asymptote occurred at pi over 2 before, it's now going to occur at pi over 4. It's going to happen twice as quickly. So when I do pi over 2 divided by 2, I'm going to get pi times a half, which is pi over 4. Half of pi over 2 is a fourth of pi. So if I pull up this and I do the 2 here, see, take a look at that. Look at how quickly the asymptote's occurring, and I can change this to pi over 4. You can see that the asymptote is occurring at pi over 4. And then the second I move it up 3, boom, that's there. again, rely on Desmos. I'm not going to be upset about it, but I just need you to realize how the asymptotes are changing, okay? And if the asymptotes are still a struggle, you know, as you're going through this, become a pro at changing the step over here on the right with the wrench and adjusting it so that way you can sort of discover where the asymptotes are, okay? So this is pi over 4 and negative pi over 4, and then it just repeats itself over and over, okay? And then I went, I guess I didn't do the up 3. So I need to go up 1, 2, 3, and then it repeats itself. Let's do another one together. So this is going to flip it. This is going to stretch it. But again, we don't really have an amplitude, but it stretches it. This is going to make it longer because remember when you find your period, you're going to do pi divided by a half, which results in pi times 2, which equals 2 pi. So our period is now 2 pi long, and with those asymptotes, you want to do the same thing. If the asymptote used to occur at a half, when you divide it by a half, you're going to get pi over 2 times 2 over 1, which is 2 pi over 2. The 2's cancel, and you get pi. So the asymptotes are going to occur at pi now. So this is negative pi and this is pi. We didn't move up or down. There's no vertical shift, so plus 0. So you're going to, and this negative flipped us. So tangent typically goes like that, but now we're going to go like this. It's hard to graph the 3 by hand, okay? I'm not going to stress about that. Okay. If I open up this right here, I'm going to have negative 3 tangent 1/2 of x. And like, take a look at, when I get rid of the negative, what's it do? It, unflips it. When I get rid of the 3, look at that. It gets kind of like fatter. So it's making it skinnier here, so to speak. It's more of a straight line. This like kind of curves and then goes up. This one is like a little more fluid, so to speak. And then you can see how the period, or the asymptotes, sorry, are at pi now and at negative pi now, okay? So as the period changes, so do the asymptotes. That's the main thing that I need you to see and realize. So let's have you do one here on your own. Let's do this one here. I wish I would have had you have done that one. Can I change this one a little bit? Let's change this one a little bit. Let's make this, let's keep it 1/2. Let's just add in something, okay? Let's add in a 4th here, x plus pi, and then we'll do -1 there. Let's make it a little more intense. So some questions popping up on screen for you to describe what each of these things are doing, okay? So pick all of the correct options. So what you should have picked was it shrank it, it made the period bigger, it moved it left, and it moved it down. Okay, so shrunk it, made it fatter, it's going to smush it in, made it the period longer, moved it left, and moved it down. Okay, so now I'd like you to answer for me, how long is the period, and where is one of the asymptotes at? Okay, so how long is the period and where is the asymptote at? Remember, it's pi over b. And if you want a little formula for asymptotes, which I haven't really written down, the asymptotes naturally occur, so to speak, at pi over 2, and then you're going to divide that by b to see how, because as the period gets bigger, the asymptote's moving. Okay, I'll just let you have a shot at that. So the b value is the 1/4. So when I do pi divided by a fourth, that turns it into pi times 4, which is 4 pi. So our period is quite large. And then when I do pi over 2 divided by a fourth, well, that's pi over 2 times 4, which is 4 pi over 2, which is 2 pi. So the asymptote gets quite large. Okay? The asymptote gets quite large. So, or, you know, not large. Large isn't really the best word, but it moves out further. Because, again, if I just get rid of everything, the asymptotes naturally occur at pi over 2. And the second I do that 1/4, you can see here how the function gets much wider because we've changed the width of the period. And as the width of the period changes, so do those asymptotes. They have to move outwards as well. And you can see there how the asymptotes are at 2 pi. That -1 moves us down 1. So if you haven't noticed, you know, the center of the function is always at 0, 0 there. And so that's a good little starting point to like sprout out from. But now it's been shifted down 1. And I said that it was a half out in front, which is going to make it like even squattier. Do you see how that happened? Like it's got a little more fluidity, and now it's kind of like flattening out even more so. And then last but not least, we've got plus pi. And you know what I'm realizing right now is that because of the plus pi, the asymptotes are moving. I forgot to, I didn't forget to mention it. I'm mentioning it now because it's the first time it's happening. But the shift is moving the asymptotes. So yes, if there was no horizontal shift, the asymptote would be at 2 pi. But the thing is when we move left pi, oh, now the asymptote is at pi. You see that? So you want to keep that in mind, and you can see there how the asymptote's at pi and 3 pi, and negative 3 pi. And we know that the length of the period, is 4 pi. And you can count it out here. 1 pi, 2 pi, 3 pi, 4 pi. The width is 4 pi. It got shifted left 1 pi. And there we go. Alright, I don't want to make this video too long. I'm getting hungry. I encourage you to screw around with Desmos, and we will obviously do some more of that in class. And enjoy the rest of your day whenever you're watching this, and I'll catch you later, okay? Have a good one.